Continuing on with significant figures, significant digits, and we're going to talk about the rules for dealing with sig figs in calculations. Now, for most of the semester, you're only going to need to worry about two rules. All right. When we get to doing things with logarithms, there is a third set of rules that deal with sig figs and logs, but we'll get to that later in the semester. For now, we just need to worry about the addition-subtraction rule and the multiplication-division rule. So we'll start with the addition-subtraction. And the rule says that the answer has the same decimal places as the fewest decimal places in the problem. All right, so the important thing about addition subtraction is we care about decimal places. All right, so let's do a little bit of example here. So let's say I'm adding a set of numbers, 15.02, 9986.0, and 3.518. This is an addition problem. All right, now, my top number has 2 decimal places. My middle number has 1 decimal place, and my bottom number has 3 decimal places. One decimal place in that middle number. So when I add all this together, when I put it into my calculator, what it spits back at me is 10004.538. All right. Now the rule says same decimal places as the fewest decimal places in the problem. So that means that I'm going to be looking at this first decimal place is where I stop. All right, I'm going to underline that. Then I'm going to look one digit, only one digit to the right to decide whether I round that number up or it stays where it is. So my final answer with this problem will be reported as 10004.5. Right, let's do another one. So let's say I'm subtracting a couple of numbers. Let's say I'm subtracting 15732.1 and 3.567. Right, this top number has 1 decimal place. The second number has 3 decimal places. So I want my final answer to have 1 decimal place. So when I plunk this into the calculator, what I get back is an answer that is 15728.533. Right, so I'm going to stop at the first decimal place. So I'm going to look right here, and I'm going to look one digit to the right to decide whether I round it up or stay where I'm at. So my final answer here will be reported as 15728.5. And it was completely unintentional that both of those problems had a 0.53 in their answers. All right, so again, just to reiterate, we care about decimal places with addition subtraction, okay? So the other rule is concerned with multiplication division. And the rule for multiplication division is that the answer has the same Sig Figs as the fewest Sig Figs in the problem. All right, notice the difference here. We're talking about Sig Figs with multiplication division. So if I, for example, multiply, let's say I want to figure out a volume of a container, and I'm measuring the sides of the container, and one side is 14.79 centimeters, and the other side is 12.11 centimeters, and the third side is 5.05 centimeters. So when I punch that into the calculator, what I get back is an answer that says 904.489845 cubic centimeters. Right, so our multiplication division rule is concerned with Sig Figs. So let's take a look. So our first number has 4 Sig Figs. Our second number has 4 Sig Figs. Our third number has 3 Sig Figs. So our final answer should have the same Sig Figs as the fewest in our problem. That's right here, 3 Sig Figs. So I'm going to be looking at my third significant digit. I'm going to look one digit to the right to decide whether I round up or round down. So my final answer here will just be 904 cubic centimeters. Now there's a reason that we do this, okay? So when we're dealing with measurements, our final answer that we report has to be reflective of the least precise measurement we take. And remember, our estimation of precision has to do with the number of significant digits. So if I have, 4 Sig Figs, 4 Sig Figs, 3 Sig Figs, that 3 Sig Figs has technically a lower level of precision. And so my final answer of that computation has to be reflective of that precision. So that's why we use these rules. Now, quite often you'll be faced with situations where you have to do complex operations. In other words, problems that have both multiplication, division, and addition, subtraction. And so the way you do that is you apply the rule by order of operations. And if your memory is a little bit fuzzy on order of operations, you may remember, please excuse my dear Aunt Sally, which means parentheses, exponents, multiplication, division, addition, subtraction. And remember, multiplication, division, addition, subtraction are simply left to right, not necessarily multiplication first or addition first. Okay, just left to right. So let's do an example. I meant to be doing examples in blue because it's nice to be consistent, but I have forgotten. So let's switch to that. Anyway, so I have an operation that looks like this. So I have 9.41 times 11 plus 9.661 minus 5.32 times 6.9437 equals what? And so I'm going to apply the rule by order of operations. So I've got multiplication, addition, and subtraction in this problem. So my multiplication comes first. And I do it left to right. So I'm going to take my 9.41 times 11, put that into the calculator, and I get 103.51. Now I'm multiplying a number that has 3 sig figs by a number that has 2 sig figs. So I need to keep track of this number at the second sig fig. Now, all I'm going to do right now is underline it, okay? I'm not going to round it yet. If you start rounding at each step, by the time you get to your final answer, you have induced a rounding error to your final answer. Okay, so you need all these digits. You need the 1, the 0, the 3, the 5, and the 1. But we're going to keep track. So that's why I underline that second significant digit. All right? So now we're going to do the other multiplication and plug that into the calculator, and we get 36.940484. And we're multiplying 3 significant digits by, what is that, 1, 2, 3, 4, 5 significant digits. So I'm going to keep track of this number at the third significant digit. Right, so now I can do the addition subtraction. So I have 103.51. Boy, that's a terrible 5. And I'm tracking at the second digit plus the 9.661 minus the 36.940484. And I'm tracking at the third digit there. So now we're doing addition subtraction problems, so I care about decimal places. This number stops at the tens place. So it has no decimals. Right? This one has 3. This one stops at the tenths place. So I'll have 1 decimal place. So my final answer needs to have no decimals. Right, so I punch these numbers into the calculator and it gets me 76.230516. Now we round. Right, I don't want to round until the very end. That's very important. If you round too early, by the time you get to the end, you'll have an incorrect answer. And I'm going to give a number that has no decimal places. So after all of that, my final answer to this problem to the correct significant digits is 76. Now, the important thing is to keep the 2 rules straight and to not round early. I highly recommend this method of using the underlining so you know where the significant digits are, but you keep the rest of your numbers and then don't round until the end. So the last thing I'm going to talk about for this particular video has most to do with lab, and it's the difference between precision and accuracy. Right? So this is important for lab because precision and accuracy are 2 different things. So precision, when it comes to doing things with measurements, is roughly analogous or synonymous really with reproducibility. Right? How close are the measurements to each other? Right? You take a series of identical measurements, all under the same conditions. How close are each of those measurements to each other? Right? If you do multiple trials, which you'll do quite a bit in your lab activities, how close are the individual numbers to each other? Accuracy, you can think of as hitting the bullseye. Right? In other words, how close are the measurements to accepted values. Right, so let's say, for example, you're trying to determine the density of a particular block of copper. And you do multiple measurements all under the same conditions, and you determine that the block of copper is 1.6 grams per cubic centimeter. The accepted value for the density of copper is, let's say, 1.58 grams per cubic centimeter. So you have a fairly high degree of accuracy because your measurements are close to the accepted value for that thing, right? Now, one of my favorite ways to show this, and it's a very common one in most textbooks, is, but I like it because it has to do with one of my hobbies, which is archery, is to use the idea of a target, right? So let's say we have a target. Right? Now, because of COVID, haven't been able to go out to the archery range for a while, and I'm not likely to be able to go out to the archery range for a while. And so let's say the next time I finally get to go, I go to the archery range, and my first set of arrows hit here, 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 and here. All right, which is probably what's going to happen. I'll be lucky to actually hit the target. But noticing that none of those arrows are close to each other, and none of them is really even that close to the bullseye, right? So in this situation, I'm neither precise or accurate, right? My arrows, there's no reproducibility. I'm not hitting the same spot every time, and I'm not even close to the bullseye. So let's say I keep shooting a little bit, and I start to get my chops back a little bit, and my next round of arrows go here, 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 and here. All right, so I'm very, very close. Each of my arrows is very close to the other ones, but I'm nowhere near the bullseye. So in this situation, I am precise, but still not accurate. So you can take a series of measurements and they're all really close to each other and you're like, great, this data looks wonderful. And then you go and you look at the accepted values and you find you're way off in left field. So you can be precise, but not accurate. So let's say I keep shooting, and because I haven't shot in many months, I don't really have the muscles to keep shooting, with any real ability. After time, I start to get tired, and my first arrow goes here, my next arrow goes here, my third arrow goes here, and my fourth arrow lands right on the bullseye. So none of my arrows are close to each other, but I did hit the bullseye. So in this case, I'm accurate, but not precise. Which is probably one of the more dangerous places to be in science, because you hit the mark once, but you can't reproduce it. Okay, so it is possible to have many different scenarios. So let's take a look at what it looks like in terms of data sets, in terms of numbers. Because most textbooks have this target imagery in it, and it's like, okay, great, I understand that, but when it comes to actually looking at numbers with your lab data, it doesn't make a whole lot of sense. All right, so let's say I have a data set that looks like this. We have one number that's 3.45. Let's say we're measuring volumes. The next number is 6.92. The next number is 2.15. And the last measurement is 11.34. Apparently somebody fell asleep during their what they were doing. And we do some calculations and we find that our average is 6.19. Our standard deviation, standard dev, is 3.95. Right? So Most students at this point would look at that standard deviation and say, okay, the standard deviation is relatively small, this must be good data. Well, it's sometimes kind of hard to easily tell how good or bad a standard deviation is just by the standard deviation. So a more useful tool for evaluating your data is percent relative deviation. And we'll talk more about how to do these things and what they mean when we get to lab. But percent relative deviation is the average divided by the standard deviation. And we do that and we get 63.8% relative deviation. Now, in order for this data to be precise, we want to be less than or equal to 10% relative deviation. Okay, 10% or under is our cutoff for being able to say that our data is precise. All right, so in this case, with a 63% relative deviation, this data is not precise. Now, our accepted value, our target value for this experiment is 15.00. So if our average is 6.19 and our accepted value is 15, we're kind of a long way off from our target value. So this data set is neither precise nor accurate. Okay, so your target value has to do with accuracy. Your relative deviation has to do with precision. Okay, two different evaluations of data. All right, so I'm going to go ahead and stop this video, and then we'll come back with a really short one where we talk about energy and kinetic energy and doing calculations there.